Hello everyone. Thank you for joining us. In today's webinar, we will discuss about the design process of a permanent magnet motor in SOLIDWORKS using MotorWizard. Our solution specialist will cover how MotorWizard can help you to achieve the results with minimum time and effort. Before discussing today's agenda, let me introduce us. My name is Armin, and I'm the sales engineer at Mworks. My colleague, Aisha, is an application engineer, and she will be delivering the technical part of today's webinar. I would like to highlight few points. During this course of presentation, if you have any question, please feel free to use the chat window to type your questions. We will answer them at the end of the presentation or will reply to you via emails. A webinar recording link will be sent to all the registrants in few days. Our agenda for today is following. I will briefly talk about our company, Mworks, where we are located, and what products we offer. Then my colleague will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by Mworks for its software users. Mworks offers 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. We have 2 office locations. Our headquarters is in Montreal, Canada, and another office in Germany. We offer 4 products in various add-ons covering a wide frequency range. Our first product is called Ems, which is used for electric and magnetic field modeling for low-frequency applications. It covers many applications like insulators, cables, busbars, permanent magnets, actuators, circuit breakers, transformers, and electric motors. Our second product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high-frequency, and high-speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is Mworks 2D, which offers statistic analysis and covers simulation of planar and axisymmetric geometries. Our latest addition is MotorWizard, which is a template-based motor design software. It offers analytical and finite element analysis of electric motors. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, Aisha will discuss how MotorWizard can be used to simulate permanent magnet motors in SolidWorks using MotorWizard. Let us briefly touch upon the licensing structure offered by Mworks. We offer 3 different programs: commercial, academic, and startup program. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the programs, our licensing structure is usually annual based. The topic for today's presentation is Boost your permanent magnet motor design using MotorWizard for SolidWorks. I would now request my colleague Aisha to take over and present the next part of this webinar. Thank you.
Thank you, Armin, for this presentation. I will take it from here. Hello, everyone, and thank you for joining us today in this webinar. Today, we'll be discussing how you could accelerate your permanent magnet motor design using MotorWizard for SolidWorks. The agenda of today's webinar consists of an introduction to permanent magnet motors and common types of brushless permanent magnet motors, or BPM, which will be followed by an overview of PM motor simulation. Next, I will give you a brief introduction about MotorWizard and why it's an adequate solution to BPM motor simulation by introducing its features to you. Next, I will be doing a software demo. After the conclusion, we'll be answering your questions. PM motors are widely used in the industry. So, what's a permanent magnet motor? A permanent magnet motor is an AC motor that uses magnets embedded into or attached to the surface of the motor's rotor. The advantages of using such a motor are the following. First, they have smaller size and weight. They have a wide speed range and thus high efficiency. They also have a high power factor and they are widely applied in the industry. There are two common types of PM motors, which are the Bldc and Pmsm motors. The Bldc motor, on the one hand, is characterized by a DC supply, a trapezoidal waveform of the induced voltage, as you can see here from the picture, an easy control and a low cost. However, due to torque ripple at commutations, it suffers from a poor performance. The Pmsm motor, on the other hand, is characterized by a sine wave supply and more complex control. This ensures, however, no torque ripple at commutation, and thus high efficiency and torque. In conclusion, the Pmsm motors offer high performance, but they are also costly. Now, to study electric machines, it's always beneficial to refer to simulation. This reduces the cost and time of manufacturing, and it's flexible when experiencing new designs and concepts. It also allows the user to find unexpected problems and phenomena. A way of simulating electric machines is using the finite element analysis, or FEA. When using the FEA method for electric machines, you are able to include complex geometries, magnetic properties of materials and saturation curves, and also winding configurations. MotorWizard is a fully embedded package in SolidWorks that is used to design 2D BPM or brushless permanent magnet motors using customized templates and simulate their characteristics, combining analytical and FEA. But why should we use MotorWizard? MotorWizard offers its user a variety of customizable PM motor templates, a vast material library, and automatic winding layout. Also, it's easy to manipulate and run predefined simulations using it. MotorWizard is equipped with multiple templates, which could be based on the stator position. So the stator could be outer or also inner, based on the slot type, as you could see here, or based on the rotor type, as you could see here. Defining the correct materials for the motor configuration is important for your simulation, and that's why MotorWizard has a wide material library. This material library consists of permanent magnet materials for the magnets, conductor materials for the winding, and also linear and nonlinear magnetic materials for the rotor and stator. After selecting the correct geometry, entering the input parameters, and defining the appropriate materials, the user enters the coil properties and can either choose a manual or automatic winding layout, which will take into account the single or double layer, and also distributed or concentrated winding layout. MotorWizard software offers the user a variety of predefined studies and results. So we can run the performance study, the no-load cogging torque study, the no-load back EMF study, the inductance study, the DQ inductance study, or the on-load study, and get the corresponding results. For instance, we have here two examples that you could get using the MotorWizard software. The first figure illustrates the efficiency map following the performance study simulation, whereas the second one illustrates the line-to-line back EMF for the 3 motor phases following the no-load back EMF simulation. I like to switch now to the software demo and show you how the MotorWizard software works. As I mentioned, MotorWizard is fully embedded in the SOLIDWORKS environment, and to be able to use it, we must make sure that it's checked in the SOLIDWORKS add-ins. So I will click on the add-ins. So we have here MotorWizard and it's checked. I will click on OK. And now to open it, I will click on Tools, EMWorks Products. I will choose MotorWizard and click on Launch. We have here 3 options. We can create a new motor design by clicking on New Design, or open an old design, maybe to check the results or run further results, or even modify the geometry, and for this purpose we can click on Open Design. Or we can also access the demo models by clicking on Demo Library. In this webinar, I will show you how to create a new motor design. So I will click on New Design and start editing the input parameters of the model. As you can see here, we can edit the model settings, the stator, rotor, and windings input parameters in the Machine Design tab. So let us first start by editing the model settings. The machine type will be brushless permanent magnet motor, and we can edit the rated parameters. The rated current is 8 ampere. The rated voltage is 220 volt. The rated speed will be 2000 RPM. The rated power will be 1500 watts, and the operating temperature will be 75 degrees Celsius. Whereas in the general sizing, we have 24 slots and 4 poles. Now we can move to editing the stator input parameters. For the stator position, we have either outer stator or inner stator. We will choose the outer stator position. We have a variety of slot types. We have either square, round, general square, or also general round for the shape of stator slot. In our case study, we'll define the slot type as general square. Before defining the stator core properties, we can preview an image of the stator core. So we'll click on Preview Image. The listed symbols are illustrated in this figure. We can set the stator outer diameter to 132 millimeters, the inner diameter of the stator to 68.4 millimeters, and the active length of the stator along the z-axis to 74 millimeters. MotorWizard also offers you the possibility to reset the default values by clicking on Reset Default Values. The slot properties are listed in this table and also defined in this figure when clicking on Preview Image. The slot properties are defined in the slot picture. The tooth gap length is 1.2 millimeters. The tooth gap width is 2.3 millimeters. The slot top fillet radius is 0.5 millimeters. The wedge height is the vertical distance of the slot wedge and it's set to 0.5 millimeters. The body tooth width is 9.2 millimeters. The slot body height will be 16 millimeters and the wedge maximum width is 4.6 millimeters. Mind you that the slot properties could be auto-computed by clicking on Auto-Compute. The stator core material is defined by default to M27 with call loss. To view the material properties or to change it to another material, click on Browse Material. You can select a material for the stator core from the vast material library. I will keep the material as default, which is M27, and then select Apply Material. To define the rotor parameters, I will click on the Rotor tab. There are different rotor types. However, for this model, the rotor type is surface-mounted with radial magnet. Now I will move to the definition of the rotor core properties. I will click on Preview Image to check the rotor core parameters. The outer diameter of the rotor is 67 mm. The inner diameter of the rotor is 32 mm. And the rotor active length along the z-axis is 74 mm. The magnet properties are listed in this table. The magnets are surface mounted. To view the image, I will click on Preview Image. The magnets are surface mounted. The magnet thickness is defined as 3.5 millimeters. The magnet angle is set to 70 degrees and the magnet fillet radius is defined as 0.1 millimeter. The offset D1 is the distance from the center of the rotor to the center of the magnet top arc and it's set to 0.5 millimeters. I will keep the rotor core material as M27 with call loss, which was defined by default, and also the shaft material, which is stainless steel. I will change, however, the magnet materials. So I will click on Browse Material. Under the Permanent Magnets Material folder, I will select the samarium cobalt and choose the first magnet material. Then I will select Apply Material. Now I will define the winding layout properties, so I will click on the Winding tab. The winding layout method can be either automatic, and in this case, the winding layout will be automatically provided by MotorWizard software, or it can be manually created, and in this case, the user should define the desired winding structure. To make it easier, I will select Automatic Winding Layout Method. The winding type can be either concentrated or distributed. However, in the case of the aromatic layout, where the pole pitch is more than 2, only the distributed winding option is active. For the distributed winding type, the number of layers in the slot can be either double or single. I will choose the single. The windings are whole coiled, and thus I will set the coil type as whole. When the number of coil per phase per pole is bigger than 1, it determines the type of coil arrangement inside the coil group. In our case, the end connection is mesh. This is the case for which the coil pitches are the same for all the coils. In this case, each coil is first wound on a trapezoidal shaped form, then The short coil sides are first fitted in alternate slots, and the long coil sides are inserted in the remaining slots. To view the winding layout, I will click on View Layout Table. You will see that the layout editor is automatically filled for the three phases, which are A, phase B, and also phase C. You can also view the layout by clicking on Display Layout, or just go back to the settings. The phasers are star connected. In the coil properties, the number of parallel paths specifies the number of the parallel paths in the winding, and in our case, it's set as 1. The number of turns per coil is 31. If the wire diameter of the coil is checked, then the fill factor is disabled. In our case, the wire diameter is set to 1.42 millimeters. The number of strands per conductor specifies the number of strands in each conductor of the winding, which is set to 1. The wire insulation thickness is 0.01 millimeters, whereas the slot liner is 0.1 millimeters. The coil material is defined as copper. After setting the desired inputs, we should click on the Validate button here. The values are consistent, as we could see here in the Details section. Now we can generate our model by clicking on the Generate Motor button. The model is successfully generated. After setting the design specifications in the Machine Design tab, and to solve the predefined studies, I will click on the Simulation tab. First, I'll save the model by clicking on Save Design. Then I will rename it as PM24S4P. I will click on Save. MotorWizard provides different results within 6 types of studies. The user can choose which result he is looking for, then check the result. To understand more, I will go through them one by one. The performance analysis, which is used to compute the steady-state performance of the machine using the maximum torque per ampere technique, MTPA. The DQ model of the machine is used to provide the following semi-analytical results, which are all versus the speed. For example, we have here the torque versus the speed result and also the efficiency map. To be able to run the performance simulation, the user should define the maximum operating current with respect to the rated value and the maximum operating speed as a percentage of the rated one. The no-load cogging torque, which is defined as the interaction between the PMs and the stator teeth. The analysis of the no-load cogging torque is important for the vibration analysis. To run the simulation, the user should first check the no-load cogging torque, then define the number of steps which determine the resolution of the desired results. Then I will switch to the no-load back EMF. The no-load back EMF is defined as the voltage generated by the magnets in the windings at a certain speed. To run the simulation, the user needs to determine 2 required inputs, which are the operating speed as a percentage of the rated one at which the result will be calculated, and also the number of steps. Then I will go to the inductance analysis. To be able to run the inductance analysis, the user should first check the inductance study. This is the FEA-based 3-phase self-inductance for the different rotor positions. The user should define the number of steps and also the operated current applied to the motor phases as a percentage of the rated one. Then I will move to the FEA-based DQ inductance plot versus the current. So, to be able to perform it, the user should first check the DQ inductance study. Before running this analysis, the user should define the number of current steps and also the operating current as a percentage of the rated one, which is applied to the motor phases. And finally, we have the FEA based on load study, where the performance of the motor is determined for a certain current. To be able to perform the no-load analysis, the user should first check it. Then, the user should define the following required input parameters. First, the user should define the source waveform, which determines the current excitation applied to the motor phases. Here, we have two options. The sine wave, which is equivalent to the case of analyzing a PM synchronous machine, and also the square wave representing 120-degree pulse and equivalent to the case of analyzing a Bldc motor. We also have the operating speed as a percentage of the rated one, the number of steps, the operating current as a percentage of the rated one. And here, in the case of a sine wave, the value is treated as an RMS value. However, in the case of square wave, the value is treated as a DC value. And finally, we have the current phase angle, which is in degrees. And in the case where the current phase angle is equal to 0 degree, the current is in phase with the generated back EMF. These parameters affect the torque values. Since the simulation takes time, I have ran the analysis and I will show you some of these results in a different SOLIDWORKS window. As you can see, the performance study is solved. We can view, for example, the torque versus the speed result by simply clicking on it. This figure illustrates the torque versus the speed plot. We can also plot the efficiency map. The efficiency map is illustrated in this figure. We can move to the second simulation tab to see the Cogging torque plot. To view the Cogging torque curve, we should simply click on it. This figure illustrates the Cogging torque versus the rotor angle in mechanical degree. Now we switch to the simulation tab number 3 to check the no-load back EMF. To view the back EMF, we should click on the back EMF curve, and the three phasors back EMF versus the rotor angle is shown in this figure. We can also view the inductance versus the rotor position by clicking on this curve. The three-phase inductances versus the rotor angle is shown in this figure. You can also plot the DQ inductance versus the current through clicking on the DQ inductance curve. The plot of the D inductance and the Q inductance versus the current are shown in this figure. We can also see the unload analysis results. It's to be highlighted that this excitation curve is generated automatically, and it's the plot of the current of the 3 BPM motor phasors versus the rotor position based on the chosen source waveform, which is in our case sinusoidal to simulate the permanent magnet synchronous motor. We can also see other results, for example, the total torque versus the rotor position by simply clicking on it. The total torque versus the rotor angle in mechanical degree is illustrated in this figure. As you saw, designing a model using MotorWizard and generating results is very simple. Let us go back now to the presentation, and I'm going straight to the conclusion. So as a conclusion, MotorWizard offers the user a variety of templates which can be based on the stator position or the stator and rotor types. The user can benefit from the vast and diverse material library as well as the aromatic winding connections which are available inside MotorWizard, and also can run MotorWizard for both the permanent magnet synchronous motor and the brushless DC motor, and also compare their performances. Now I will give the presentation back to my colleague Armin, and at the end we'll be answering your questions. Thank you very much, everybody.
Thank you, Aisha, for your presentation. And now I would like to have a quick overview on Ems software. Ems product offers electrical and magnetic solvers. In addition, few multiphysics options are available with this product, like thermal, motion, linear statics, and circuits. Ems software is available in 4 packages: electric, magnetic, professional, and premium. To get more information on the software packaging and pricing, you can connect with me after this webinar. Now, let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into 2 categories: applications related to low-frequency simulation and applications related to high-frequency simulation. Within low-frequency category, we offer 3 products: EMS 3D, EMWorks 2D, and MotorWizard. These products can be used to design and simulate applications like cables, insulators, bus bars, solenoids, magnet arrays, eddy current braking, wireless charging, transformers, electrical machines, etc. Within high-frequency category, we offer 1 product, HFWorks. This product can be used to design and simulate high-frequency applications like antennas, waveguides, filters, resonators, connectors, etc. To get more information on the software packaging and pricing, you can connect with me after this webinar. EMWorks offers various free learning resources. Within the software purchase or trial, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all users of EMWorks software. I encourage everyone to try our software and experience its capabilities. Upon trial request and user qualification, we offer 2 weeks of free access to the limited version of the software. In this limited version, users can access many predefined model examples and tutorials to learn about the software features and capabilities. To request for a trial license, visit our webpage www.emworks.com. Go to our Contact Us page, fill in your information, and submit your request. One of our representatives will reach out to you. I would like to thank you all on behalf of EMWorks for participating in this webinar. A webinar recording with the webinar feedback survey link will be sent to all the registrants in few days. We appreciate your time to fill out the webinar feedback survey, as it helps us to improve our services and know what are your interested topics for our future webinars. Feel free to contact us after this webinar to get more information on this product. Thank you.